In this video, we are going to look at correlational analyses as well as regression. And there's a lot of information in the module as well as the textbook, so I'm going to keep the introduction relatively short. But essentially, correlation allows you to look at the strength and the direction of relationship between two variables, x and y. And what we can then do is construct the linear equation, which is going to essentially allow us to make predictions of y using x values with the least amount of error. At least that's one way of summarizing it. And so let's look at this first problem. And we're going to go through a bunch of different processes here because there's a lot you can do with correlation. It's one of the most common statistical analyses in the social sciences. So here we go. For the following scores, calculate and interpret the Pearson correlation, R, to determine the strength and direction of the relationship between servings of vegetables per week, X, and hours of exercise per week, Y. Next, construct and interpret the linear equation. Finally, test conduct a two-tailed hypothesis test to see if the correlation is statistically significant using alpha of 0.05. Let me just fix that typo. Okay, so let's talk about what we're doing here. First and foremost, we have two variables. Vegetable consumption per week, so like how many servings per week, and exercise. And in this study, we have 6 people. There's n equals 6 individuals in our study. And so I'm going to put that here. And how did I get that? Well, there's one person who had 10 vegetables servings per week, and they exercised 7 hours per week. The second person was 4 vegetables and 3 hours of exercise. The third person is 0 and 3, and then the fourth is 1 and 6, etc. There's 6 people total. And what we want to know is, essentially we're asking, is there a relationship between these two variables? Do those who eat a lot of vegetables tend to also exercise a lot? And I also think it's worth noting, the all-important phrase, correlation does not imply causation. So in this case, let's say we do find a significant correlation here. That means, simply put, that vegetables are associated with exercise. It does not mean that vegetables causes exercise or exercise causes vegetables, because most likely what's going on is that there's some third variable that is driving the relationship between these two. So for example, conscientiousness. If you're extremely conscientious, you're probably more likely to eat vegetables. And if you're conscientious, you're also more likely to exercise. So if you want to know about cause and effect, you have to use an experiment, an experimental design, maybe an independent samples t-test or something like that. But here, all we're looking at is a relationship, a pattern, or an association between X and Y. But we can look at the strength of that relationship and the direction of that relationship. And we're going to use the Pearson correlation, which is noted with the symbol R. And again, in brief summary, because there's plenty of more detail in the textbook as well as in the module, R is a ratio. And on the top, this value called SP, that's an indication of how much X and Y move together or co-vary. And on the bottom here is an indication of how much X and Y are moving independently of one another, or separate variance. So if R is really large, that tells us that there's a strong relationship between these two variables. And if R is really small, close to 0, that means that there's a very weak relationship between X and Y. All right, so in order to calculate R, we need some preliminary information, which I've actually already gone and calculated before this video. Now let me break this apart for you. We still have the 2 original columns, vegetables X, I just put it here, and exercise Y, which is right here. And I've done some other work in between. So this column right here is the deviation scores for X. So what I did was I calculated the mean of X, which was 24. 24 is the sum of the scores here. And so 24 divided by 6 gives me a mean of 4. And then I subtracted 4 from every X value. So for example, 10 minus 4 is 6. 4 minus 4 is 0. These are the deviation scores. And those are going to be important in a moment. But then, of course, when you square those deviation scores and sum the squared deviation scores together, you get the sum of squares. In this case, sum of squares for X is 102. I did all that same stuff for Y. So Y has a mean of 5 if you calculate the mean. And these are all the deviation scores, which means I subtracted 5 from each score. And then when you square those values and sum them all together, you get sum of squares for Y equal to 74. Okay, so before we talk about this last column, let's just note we already have a lot of what we need for our formula for R, the Pearson correlation. Specifically, in the denominator, you have sum of squares for X, which is 102, and sum of squares for Y, which is 74. What we need up here in the numerator is SP, which stands for the sum of the products of deviation scores. So that's what this column here is for. And look at the heading. I'm taking the deviation scores for X and multiplying them by the deviation scores for Y. So over here is my deviation scores for X. Let me actually create or highlight them just so it's didn't work. Why isn't that working? Okay, never mind. We're not highlighting. Just kidding, we are. Got to use my stylus. So those are my deviation scores for X. Here are my deviation scores for Y. Essentially, I want to multiply them together for each person in my study. So for the first person, their deviation score for X values was 6. The deviation score for Y values was 2. 6 times 2 gives me 12. You do that for every individual, and you sum them together, and it gives you 67. This, again, is an indication of how much X and Y are co-varying or moving together. All right, so let's go ahead and calculate our Pearson correlation, which is R. R is equal to SP, 67, divided by the square root of your sum of squares for X, which was 102, multiplied by your sum of squares for Y, which was 74. So that little dot right there is a multiplication symbol. Let me make a parentheses actually just to make it a little more obvious. Okay, so let's go to our calculator, find out what we have here. And I'm getting 0.77. Is the correlation between X and Y. So first and foremost, this is a positive value. That means that the correlation between X and Y is positive. Positive correlations mean that as X goes up, Y also tends to rise. Whereas, well, also, real quick, a positive correlation means that they move in the same direction. So as X goes down, Y goes down as well. If it were a negative correlation, which it's not, but if it were a negative correlation, that would indicate that increases in X are associated with decreases in Y. But we got a positive correlation, which means they move in the same direction. Now, how strong is that correlation? One of the formulas that's not listed here for you, but it's something that we've used a lot, is R squared. We don't need the formula here because we already have R. So if you square R, you get 0.59. And recall from earlier modules, a value of 0.25 is considered large, or in this case, strong. So we can say that there's a very strong positive correlation between vegetable consumption and exercise. Okay, so that's the first part of this problem where it says calculate and interpret the Pearson correlation. It's 0.77, which is positive and very strong. Those are the interpretations. It says next, construct and interpret the linear equation. So essentially the idea behind the linear equation is you're trying to find the best fit line. If you were to plot the data and find the line that describes the data best, the regression line is the one that essentially has the least amount of error, so that you can plug in values of x and it spits out predicted values of y with as little amount of error as possible. Because one of the great things that you use correlational analyses for is predictions. You plug in x, it gives you a predicted value of y. So to do that, we need to construct this linear equation, which you probably remember this from back in algebra. B, in this case, is the slope of the line. It tells you how much y changes for every point of a change in x. And then A is our y-intercept. It tells us what y equals when x is 0. All right, so we need to figure out what B and A are, and here are your formulas. Let's start with B. B is equal to SP, which is 67, over the sum of squares of x, which is 102. And that gives us 0.66. Then we get A, which is the mean of y. Although I didn't put it here, the mean of y, let me actually put it in the appropriate spot. The mean of y, you add up all the values and divide by 6, since there are 6 of them, gives you 5. So we know that the mean of y is 5. Subtract b, which is 0.66, multiplied by the mean of x. The mean of x, as discussed earlier, was 4. And so we can calculate a now. And I'm getting 2.36. All right, so now here we can construct the linear equation. Y equals 0.66 times x plus 2.36. That's it. That's our linear equation. And so what we can now do, if we wanted to, is plug in hypothetical values of x to determine what y might be in that case. So for example, let's say, what about x equals 2? If x equals 2, what will y be? At least, what is our prediction of y with the least amount of error? So if somebody eats 2 servings of vegetables per week, what can we predict is the amount of exercise that person has? And so essentially all you do is plug in an x value of 2 into your linear equation to predict y. And so our predicted value of y is 3.68. So basically what our data is telling us is that for individuals who have 2 vegetable servings per week, we would expect them to have about 3.68 hours of exercise per week based on this sample data. All right, there's one final thing we can do, and that is to test the significance of our correlation and regression equation. In other words, all the calculations we've done so far have been based upon this sample of 6 individuals in this study. But we can now use inferential statistics to see if that is a statistically significant correlation, In other words, is this something we would expect in the entire population that these 6 people came from? So let's do a two-tailed hypothesis test, which is basically just checking, is there a significant correlation or not? The textbook talks about one-tailed tests, which are, all the steps are essentially the same except for the hypotheses, which in a one-tailed test, you're making a prediction that the correlation is either positive or negative. Here, we're simply checking with a two-tailed test if the correlation is 0 or not 0. So your hypotheses look like this. The hypothesis says that the population correlation is equal to 0. That's the null hypothesis. And this symbol right here is rho. It looks like a P. It's the Greek symbol rho, which is the symbol used for population correlation. And the alternative hypothesis, H1, is saying that the population correlation is not 0. It is a statistically significant correlation. It's not 0. All right, so what do we need to do? We need to calculate our test statistic, which is T. And here's what T is all about. You have your sample data compared to some measurement of error. There's your error term right there with 2 degrees of freedom. So basically this is inferential statistics. It's a hypothesis test, which means we have our test statistic T, and we're going to compare that to some critical value from our T table. So let's go ahead and find that critical value first. And what we need is our degrees of freedom. So with this correlational analysis, degrees of freedom is n minus 2. Since you need at least 2 data points in order to describe a linear relationship, that's why degrees of freedom is n minus 2. Anyway, 6 people in our study, degrees of freedom is 6 minus 2, which is 4. And we're using an alpha of 0.05, 2 tails. So let's go ahead and find that on our table. So 4 degrees of freedom, see where that matches up with alpha of 0.05, 2 tails, looks like a critical value of 2.776. It's going to be plus n minus because we're doing 2 tails. So let me go ahead and write that here. Our critical value of T is plus n minus 2.776. All right, let me just kind of separate this. So now let's go ahead and calculate the test statistic, our T value. We take our correlation, our sample correlation of 0.77, and divide by your error term. And the error term in this case is 1 minus your correlation squared, so 0.77 squared, over degrees of freedom, n minus 2, which we calculated as 4. All right, so let's go ahead and do that. I'm getting 2.41. Oops. .41 is not in the critical region. In other words, it does not exceed 2.776. So our conclusion, therefore, is fail to reject H0. Essentially, what that means is that this data does not suggest there is a real population correlation. In other words, this correlation from our sample is probably just sampling error. Now, I think that's interesting to consider for a moment because we had this sample with a correlation of 0.77 and our effect size told us that it was a very strong correlation. Yet, when we calculated the test statistic, it was not significant. And so the reason for that is probably that we had a really small sample size. With only 6 people, there's just too much error. So one of the rules in social science research, probably I think any research to be honest, is Larger samples are better because the larger your sample, the more representative that sample is of the population. In other words, larger samples bring about less error. So this error term down here is just too large. It biases the study, and therefore I would guess if you had data on a larger sample, you would probably find a statistically significant correlation between vegetables and exercise. Nevertheless, the data are what the data are. So we happen to find a fail to reject the null hypothesis with this data set. Okay, so there you have it. As always, I want to encourage you to do more problems from the textbook. The authors go step by step with a number of examples. Also look at the study guide and let me know if you have questions.